in order to start speaking about designing synchronous sequential circuits, there are two issues that we would like to explain. One is called state reduction, and the other is called state assignment. State reduction problem is the process of reducing the number of flip-flops in a sequential circuit, but maintaining the external input-output requirement unchanged. We know that a sequential circuit that has m flip-flops will have 2 to the m states, and reducing the number of states may or may not result in a reduction in the number of flip-flops. However, it is useful to reduce number of states because it may reduce number of flip-flops, or at least it will make the combinational part easier or less hardware. The state reduction problem, in order to understand it, let us look at the state diagram of the circuit that we see here. It has 7 states named A, B, C, D, E, F, and G. And in order to understand the input-output relationship of the circuit, we assume that the circuit is initially in state A. So we assume the circuit is here, and we let the input sequence be what we can see on this slide. Now, we will derive the complete input-output sequence for the circuit as follows. When the circuit is in state A, if the input is 0, which is this first bit here, looking at the diagram, we find that the circuit stays in state A and the output is 0. So we write here A and the output is 0. Now, when we are in A and the input is 1, where will the circuit go? We see that the circuit goes to state B here when the input is 1 and the output is 0. We write B here and we write the output is 0. Now in state B, when the input is 0, we look at the circuit here, we find that it goes to C. So we write it goes to C here and the output is 0. So we write the output 0 here. And when it is in C and the input is 1, we look at the diagram, we find it goes to D and the output is 0. So we write D here and the output is 0, and so on. Actually, when we are in D and the input is 0, we goes to E and the output is 0. So we write E here and 0 here. And when if the input is 1, it goes to F and the output is 1. Here, E goes to F. If the input is 1, out is 1. And if we are in F and the input is 1, it stays at F and the output is 1. So it is right here, 1, 1. And so on we continue. We find that for this input sequence, this will be the output sequence. Now, let us look at the state reduction. First, we define 2 states to be equivalent if for each member of the set of inputs, they give exactly the same output and send the circuit either to the same state or to an equivalent state. And the algorithm for state reduction, we do the following. First, we find the completely specified state table for the circuit, as we can see here. This is derived from the previous state diagram directly. And second, when 2 states are equivalent, we keep only one of them and we remove the other. And when the removed states are used in the next state columns, we change them with the equivalent state symbols. So let us look at the state table here, at the states A, B, C, D, E, F, G. State A goes to A and B, and these are the outputs for the inputs 0 and 1 respectively. State B goes to C and D with these outputs 0, 0. C goes to A and D with these outputs, and D goes to E and F, output 0 and 1. E goes to A and F, output 0, 1. F goes to G, F, output 0, 1. And G goes to A and F, output 0, 1. So, are there 2 states which give the same next state and the same outputs? If we look carefully, we find that states E and G both go to A and F for the inputs 0 and 1 and give the outputs 0 and 1 respectively. Therefore, we say that states A and G are equivalent, which means we can remove one of them. Let us remove state G here. So we don't have G. When we remove G here, we look at the next state, these two columns. When G is there, we replace G with E. We find G is here. So we erase G and we write E. And this is now a reduced state table with 6 states only instead of 7. Let us look at this, make it cleaner to this table, which has 6 states: A, B, C, D, E, and F. And as we said, G is already gone. Now looking at this table again, let us see if there are other states that are also equivalent. We find that state D goes to E and F and the output 0 and 1, and state F goes to E and F and the output is 0 and 1. Therefore, D and F are equivalent. Again, we remove one of them. Let us remove F. If we remove F, so F is no longer there, it should be replaced by D wherever it appears. So we have F here, we write here, and we write here D, and this will be the new state table with only 5 states, A, B, C, D, E. Again, we write it here in a cleaner way. State A goes to A and B, B goes to C and D, C goes to A and D, D goes to E and D, and E goes to A and D, and these are the outputs as we can see in this table. Are there any two equivalent states here in this table? Let us look at these. We have A and B next state, C and D, A and D, and E and D, A and D. Oh, A and D is the same here as here. Are these equivalent? No, because the outputs are different. The outputs here are 0 and 0, and the outputs here are 0 and 1. Therefore, this state table actually is the reduced one. We cannot reduce it further. Now, for this state, I'm going to draw the reduced state diagram actually, which is derived from this table. We just write down the 5 states A, B, C, D, E, and we write the arrows from the previous table that we have just seen. A goes to A when input is 0, output is 0, and A goes to B when input is 1, output is 0, and so on. And this table is the reduced version of this table here that we started with. Now, in order to show that these two circuits are exactly the same, we can take the same input sequence that we have taken earlier, which is this input sequence. It is what we applied earlier to this state diagram here, and we apply this to the new state diagram here without doing it actually. If we start in state A and the input is 0, we stay in A and the output is 0. And if we are in state A, the input is 1, we go to B and output is 0. All this we take it from this diagram here. And for B, if the input is 0, we go to C and output is 0, and so forth. We find the output here. And comparing this output with the output that we obtained earlier for this original circuit, we find it exactly the same. Therefore, we said that the same output sequence results, although the state sequence is different, of course, because there are two states here. F and G are no longer in this state diagram here. And of course, doing this, we simplify the state diagram from 7 states here to 5 states here. Now, the next problem is called state assignment. State assignment simply says assigning binary values to the states. That's what it means. A process of assigning coded binary values to the states. Here we have 5 states: A, B, C, D, and E. And for 5 states, we need a minimum of 3 flip-flops, because with the 3 flip-flops, we have 2 to the power 3, which is 8 different states. We use 5 of the states for A, B, C, D, and E, and the other 3 will remain unused. There are so many different combinations for the assignment. One of them, we can assign the values 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0 to the states A, B, C, D, and E respectively. Or we can assign a gray code like assignment, which is 0, 0, 0 to state A, 0, 0, 1 to state B, so we have 1 change, and 0, 1, 1 to state C, which is 1 change, this second bit, and 0, 1, 0 to state D, so this bit changed, the first one, and 1, 1, 0 to state E. Or we can assign what we call one hot assignment, which means always we have one flip-flop that is 1, which is hot, because 1 means 5 volt, and 0 means not hot. So A can be 0, 0, 0, 0, 1, and B 0, 0, 0, 1, 0, C can be 0, 0, 1, 0, 0, and so forth. And of course here we need 5 flip-flops as compared to 3 flip-flops in the previous 2 assignments. Now, we assign binary values because in the design we use binary coded state tables. Therefore, for this table here that we have obtained earlier for the reduced state diagram, we would like to have the reduced state table. So we write down the states A, B, C, D, E, present state 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0 if we choose this first assignment 1. And for state A, it goes to A or B. As we can see here, A goes to A or B, and it will go to 0, 0, 0 or 0, 0, 1, and the outputs will be 0 and 0. And state B will go from the diagram here, will go to C or to D for input 0 and 1. So we write 0, 1, 0, which is C, or 0, 1, 1, which is D. And state C here goes to A or D. So we write 0, 0, 0 and 0, 1, 1. And then state D here goes either to E or D. So it goes to 1, 0, 0 or 0, 1, 1. And finally, state E, which is 1, 0, 0, goes to state A, 0, 0, 0 or to 0, 1, 1. And the outputs will be as we see from this diagram here. This binary coded state table is what we use actually in the design of sequential circuits, which we will discuss next.